Up next, Abdul. Abdul Bezrati is a senior engine programmer on the render team. Has worked on our effects system, our imposter system, our material graph system,
Textures,
textures.
models, pretty much everything rendering related.
So let's get to the concrete really quick. Draw calls. I know that's always a question. How many draw calls?
The fewer draw calls that we do, the better.
But how many do we do?
Oh, it depends
That's
on-
everybody. That's what everybody wants to know.
Well, right now in a typical scene in Spider-Man and the PlayStation 4.
Well, we should probably talk about a different game.
So, okay. Well, it's
Let's
work
call
in
it.
progress.
Let's say Sunset.
Okay, let's talk about Sunset Overdrive. So basically, before we shipped Sunset Overdrive, a year before we shipped it, we were running into performance issues, and the reason for that is because we were dealing with a lot of draw calls. Just to give you an estimate, sometimes in Sunset Overdrive, you can climb up all the way to the top of the building and like look down the city and look at everything in the background, and we were running around 17,000 draw calls, and we're not talking about shadow casting, we're just talking about just G-buffer forward rendering, which did hurt performance a lot. We're talking about 10 frames per second, and it was terrible. So the idea was to communicate with art and tell them to, hey, can you actually reduce a draw call by batching things together using atlases? And that was tedious because it takes a lot of time. It just puts a brake on iteration process. You can't iterate, you can't imagine certain things, and it was just not going to happen. So in comes instancing where basically models and subsets that share the same materials, same meshes and all that stuff are grouped together, sorted together, and submitted to the GPU in one batch. And we went from 15, 17,000 draw call to a more manageable 1,000, 1,200, and the frame rate went from 10 frames per second to, in that particular shot that I have in mind, to 28 and 29 frames per second, which is just one frame short of what our goal was, So yeah, draw calls, the fewer the better. Yeah.
Another question that had come in was about, I think, was about dynamic resolution. And we had, in terms of dynamic render resolution in Resistance 2, we had done sort of a dynamic adjustment of resolution. But I don't think it's something that we've really done since.
Well, we experimented with dynamic resolution on Sunset Overdrive on Xbox, but I believe it was a very late solution, and Al Haston, our technical director, decided we're not going to go with it, but we did have it up and running at one point. Sunset Overdrive shipped at 900p, but our dynamic resolution went all the way up to 1024, not 1080, 1024, something like that, a magical number, and it was like dynamic. We never dipped under 900p, but we actually scaled all the way up to 1024, depending on the scene. But like I said, we never shipped with it. We thought that it was a little too late in the pipeline to make the game, and we had just a crap ton of stuff to fix to ship, so it took a back seat.
I know on Resistance 2, where we did do this, one of the things that we found is, we ended up sort of having fixed resolutions that we swapped between, because we found that sort of these interim resolutions actually looked worse, right? That we couldn't do a smooth change between two because there was just really bad looking ones in between.
Well, what we did, I believe, in Resistance 2, and it's been a few years since we did the Resistance 2, it depends on the scene. Like, we scaled the resolution when there's a lot of fire effect, explosions, radial blur, and things like that, which actually did hide the downsampling and then the upsampling of the resolution. So when the scene is so busy and when you're like shooting at aliens and shooting back at you, the last thing that you're doing is just trying to isolate a certain pixel and see how it looks when the resolution goes down or goes up, So it was very specific scenarios, and the scenarios that we created the solution for worked out.
I think
pretty
you
well.
just presented a challenge to some particular group on NeoGAF.
Just pause and then look for the bed resolution. Yeah, Digital Foundry will do that.
So let's talk about imposters, right? When we talk about
Okay.
an open world like say Sunset, how many? What is an imposter? How many are we talking about? How is it built? How does
All
it
right.
work?
Let me give a brief introduction. Basically, even though we were given 5 gigs of RAM to actually work on the Xbox One, the PlayStation 4, coming up from a system that has only 512 meg, that's huge, like 10 folds. And yeah, let's just fill up that memory with as much stuff. We're not going to be like running against any walls. There's plenty of memory, but that's just not going to happen. Basically, we ate up that 5 gigs and asked for more. And like, especially in open world where we have like a large city in Sunset Overdrive, where you can just stand anywhere and see miles and miles down. And there was no way for us to keep all that memory, all that content resident in the 5 gigs that we have. So what we end up doing is divide the world into tiles, let's say 100 meter by 100 meter tiles. And we loaded the 9 tiles the closest 9 tiles to the hero. Everything else gets streamed out, but when streamed out, those are assets that evacuated from the memory, and we have to have something actually that's there that meets two criteria. First of all, it has to look similar to the asset that's being replaced, and actually 3 criteria. It has to look similar, it has to be light on the memory, and it has to render wicked fast. So basically what we did is, for every building that we have, we create an imposter where we take all the geometry, all the model instances, and we're talking about hundreds of model instances that make up a single building, and bake it into a simple mesh and decimate that mesh to as few triangles as possible.
But this is an automated process. We're not manually
Correct.
creating an LOD here.
Correct, we're not. We're just taking up all those model instances and putting a volume around it. That was the approach that we had in Sunset Overdrive. We have a different approach now, but let's talk about what we shipped with. So we basically place a volume around building or build-ins, and then all the model instances within that volume are basically baked together into a single mesh that produces a million vertices. And then we decimate that down to a manageable 30, 20,000 vertices. And as for textures, because buildings are made of, like I said, hundreds of models that have 2, 3, 4 materials each, so we're talking about hundreds of materials as well, thousands of materials. What we did is we actually captured the final color from top, left, right, front, back, and sometimes from underneath the buildings, because sometimes buildings have parts, elements stick out of it, and we need the information that's under the buildings. So we captured the pixels, and we captured a low-resolution version of the buildings, and we projected that image on the building and displayed it. And it allowed us to keep a high fidelity in the distance, and it just runs super fast.
So you have an automatically generated, sort of decimated, low geometry density model,
Mesh, correct.
and sort of this cubic projection texture.
Indeed.
Are those UVs generated, or is it just that cubic projection happening at runtime?
The very first thing that we did was actually to generate the UVs by doing the projection and all that stuff offline, and then load it up. And it actually did work for Sunset Overdrive, because we had, let's say, 1,000 imposters, maybe like 1,500 imposters in the entire game. But in Project X, 10 times as much. So we could not afford to have that extra stream of information. And what we did is the same process that we generated the UVs with offline, we actually do it in runtime through the vertex shader, where we actually sample the whole triangle in the vertex shader, generate the normal. So we're not even storing normal. We generate the normal on the fly in the vertex shader, and then generate the UVs out of that and pass that as interpolants to the pixel shader stage. And that saved a lot of memory, and yeah.
All right. One of the things that I also want to talk about is your work on helping us manage our sort of specific hardware GPU targets in particular. As we are cross-platform, and we are managing not just, say, the PS4 target, but also our Oculus PC targets, and previously our Xbox
One.
So how, from our point of view, right? How do we manage the multiple targets from rendering?
Well, life used to be so simple. We had just one platform and we targeted that platform, but those days are long gone. And now, for instance, going from a title that runs on the PS4 to a title that runs on the VR headset, we do have to disable certain elements. You know, the quickest, I mean, there's two things. You can either disable certain elements to get your frame rate back and run at 90 frames per second on Oculus, or you can spend time to actually generate a new solution that is not as heavy on resources, especially GPU time, and implement it. We've done both approaches. We disabled certain elements of our full engine that ships on the PS4 and just single monitor games. And we also developed solutions specifically for the VR. So for instance, we're talking about global illumination. The way we did global illumination in PC, it's just super high quality, takes a lot of time. It uses deferred computing on the PS4 to eat the cost. On the PC, we don't have that much of a problem because we're targeting certain powerful GPUs, but when it comes to rendering to two viewports on VR, it's just the solution wasn't gonna fly. It would take in about a millisecond in each eye. 2 milliseconds, you're basically eating up roughly 20% of all of your GPU time for something that might or might not contribute well enough to your game. So we came up with a lightweight solution that doesn't take as much memory, but specifically doesn't take as many GPU cycles to actually render. So that was the other solution.
I think, to generalize that a little bit, I think it speaks to our sort of philosophy towards cross-platform, and it's not really about creating an abstraction of, say, the hardware that we target, but rather sort of a collection of commonalities that we target, and then where it makes sense to do something specific, that's what we do.
That is correct. Sometimes we will spend the time to actually have something target a specific hardware, but 99% of the time we're just going to go for the common, like the lowest denominator, and go with that.
The common definition, right? The stuff
Correct.
that's common across everything, right, that we're targeting. But in terms of sort of like the actual design, right? Like say the API for rendering, how is that managed?
Here's the thing. I'm going to talk about developing for like porting our engine to PlayStation 4. So it's real experience. Basically, Jonathan and I were given the task to, here's a dev kit, just get our engine running on the PlayStation 4. So reading through the documents and all that stuff. And then I realized that our engine relies on DirectX 11 on both PC and Xbox One, and pretty much everything scattered through our rendering files is either like DX11 or specifically tweaked for the APIs of the Xbox One. And I thought it would be easier just for me to write a wrapper around the PlayStation 4 API that just DX11, and that's what I called it, Orbis DX11. And it worked. Like, it only took us to get something up and running and get 90% or 95% there, like 3 weeks worth of time. And we didn't have to change that many files. We only have like a handful of PlayStation 4 files. Everything else just follows DX11. So set pixel shaders, get pixel shaders, set OM render targets, you name it, it's implemented. And it was easy, it was quick, and kind of makes you appreciate those who write drivers for NVIDIA and AMD hardware. It's cool.
Speaking of vertex shaders and fragment shaders in particular, one of the things that's changed, that we kind of touched on, that's changed over time, is our push to putting those kinds of things into the hands of artists, right? And we're not the only engine. There's it's a sort of popular approach now, right? To sort of like a graph shader to develop that kind of thing. When you were developing that system in particular, sort of the graph shader model for materials, what was the most sort of surprising result?
The most surprising result is the quality of the shaders that our fellow Insomniacs artists generated. Like, sometimes you think that people are just used to Maya and they're not going to be able to produce the results that a dedicated graphics programmer can come up with, but it was surprising that they could generate some mind-boggling graphics. I mean, it's pretty awesome.
So if we're going to talk, let's talk about concrete counts again, right?
Mhm.
How many, when we first implemented this, how many, say, unique shaders
Oh,
did you
yeah.
expect people to develop?
Actually, I'm thinking about more things that were surprising. So one of them was, let's step back a bit. The old engine, all the shaders were actually written by programmers, and artists could access them through drop-down menus and checkboxes as an enable diffuse map, enable gloss map, change this is what tint should look like, and so on. We decided to go away from that because the iteration time was just heinous. Somebody would come up, an artist would come up with a shader idea, and a programmer needs to implement it and then tweak it, refine it, make a tool release, and then collect feedback, and then work on it again, and then send it back. It was just inefficient. It's just, we were not going with that approach. So in comes the custom material graphs and shader networks, and everybody can just create their own material graph, their own shaders, anytime, iterate, test, and put it in the game. So we thought, because initially when we were doing the fixed pipeline, we had like 64 materials, maybe like maybe 32 unique material with some variation to it. And we were expecting that people were gonna create maybe like 32 master material graphs and then just use those and then do some variation on those, because we have materials that can override parts of the material graph, so you don't have to generate multiple material graphs. You can just generate multiple materials that reference the same material graph. So 32 was 64 maybe, like if we're being pessimistic, but we're over 2,000 material graphs, so WTF, That's right. It was crazy, but at least they're able to prototype, they're able to work on what they want and see the results right away, iterate over it, bounce ideas, experiment with novel gameplay, feedback, and yeah.
One of the, I think, the fears in
Mhm.
general of putting out a system like that, and again, we're not the only ones that do it, is that you're not going to be really able to push the edge as much. You're not going to be able to optimize those kinds of things if you have people who are sort of not experts in that sort of optimization space, working on the visual.
Mhm.
And just sort of responsible for what is effectively writing code.
Mhm.
However you disguise it, right, in terms
Mhm.
of a graph shader, it is code.
Mhm.
So what ultimately, what's the result? Ultimately, sort of looking back now, was that fear founded? Is it a real issue?
That is a real issue. To give you an example, one of our most used shader is a shader that has so many parts that are not active 90% of the time. For instance, we have a global environment shader that also can simulate puddles and rain and other attributes like even custom ambient occlusion, you name it, world space normal maps instead of just the place normal maps on models, and all those parts in the material graphs are active in one instance or the other. And the way they activate it or deactivate it, at least just as of a few weeks ago, was to do lerps or doing selects and things like that. And all of that is being dynamically evaluated on the GPU. So we're pretty much paying a huge cost for parts of the look that we're not actually seeing. I mean, I'm looking at a wall, there's no puddle on the wall, and yet we're paying a little bit of a cost because of that. So my fear was founded, but that encouraged us to actually seek an alternate solution. So instead of splitting that material graph into 4 or 5 variations, and we decided to implement variation nodes into the material graph, where given one single asset, it can generate up to 4 billion variations and store it and select the one that is actively bound. And that way we minimize the number of assets and we reduce the complexity and we only pay the cost when we need to.
So speaking of generating 4 billion variations, the sort of explosive combinations here is also a practical issue, right? when you're talking about sort of the combinations of, you know, what you're generating code per platform, and in terms of variations when I'm turning on things on and off, and those are all generating various combinations of shaders, and how much, you know, potentially how many bits of code that you're spreading out from this one graph. How is that sort of potentially explosive combination managed?
Well, the size of the compiled pixel shaders and vertex shader, domain shader, hole shader, you name it, they're not that big. And we try and tell people to limit themselves to 5 or 6 variation in the material graph, because that's basically 32 to 64 actual shaders times vertex shader, domain shader, hole shader, and pixel shader to generate. And it's not just a matter of disk space, because it's not really that bad. It's more of a compile thing, because these shaders need to be compiled. So we're compiling, first of all, the pixel shader to determine how many interpolants, lean interpolants, are feeding into that pixel shader. And then we walk down the whole shader, domain shader, whole shader, vertex shader, and compile those, and then go all the way back up to the pixel shader and compile it with all the optimization and all that stuff. So it takes about 1 second to 2 seconds, sometimes 3 seconds, depends on the complexity of the material graph. So if it's 3, and that's per LOD. So if we have 2 LODs, that's 6 seconds for a complex material graph with no variation. Now, enter variations. If you have 1 variation, you end up paying twice the cost. If you have 2 variations, 4 times the cost. And so, I mean, it's not really 4 times the cost, but it's roughly around that, you know, because the variation can disable a complex part that can trip the compiler or not, you know. So the worst case, the reason we came up with a 5 to 6 variation max is because when I first implemented, I let complete control up to the artist. Hey, add as many variations as you want. Somebody went in and added 12 variations. That 12 variation caused like 4,000 material graph, 4,000 shaders to actually be generated. So around the 9 or 10 minute of compiling, I pulled down, pulled up the calculator and started like trying to guess how long is that gonna take. And I'm like, it's gonna be taking like half hour. So yeah, hell no, I'm not gonna be waiting for that, you know? Yeah, so an email went out and be like, yeah, so let's not exceed 5 or 6, you know? And even with that, right now in DevTrack, I have a bug says that this shader is taking forever to compile, which is 2 minutes, you know? And you look and you see like 4 or 5 variations, just really complex shaders, but you have to manage. Mm-hmm.
Jonathan, do we have anything?
Okay. How is the decision made to integrate a new rendering technique into Core? What group drives that choice?
So the question is, how is a decision to integrate a new rendering technique decided?
Yeah.
And
Who drives
who drives the choice?
Here's the thing. We don't go and actively hunt for techniques, as in not the render team. We don't go around looking for techniques to implement, but fellow insomniacs will shoot us an email. Hey, have you guys seen this game? Have you guys read this paper? Have you guys been to GDC, SIGGRAPH? There's really cool paper that comes out, you know, and it's mostly art people that bring it to our attention. And then we look at it and we're like, hey, this could work pretty well in the context of the games that we're actually working on. You know, let's see who implemented it and how long it took to implement, the complexity, the cost, the return on investment, and all that stuff. If it's just one tiny effect in a corner somewhere, you know, there's no real purpose of actually spending the time and the effort to implement it. But if it's something that you actually see all the time and you notice and all that, then we decide, okay, let's put a timetable and see how long is that going to take us to implement. You know, if it's going to take a fair amount of time, like, then let's go for it. If it's just going to take too much time, we can always pull back and say we're not going to do it.
So, but I think that, you know, so the heart of your answer is that, one, we're not looking for tech just for tech's sake, right? We're looking at the games in context and what we're trying to make and talking to the art teams about what we want to accomplish. We're very much a development-driven team. And so those decisions are based on what we want to see in the games as opposed to just some tech that we want to make.
Indeed, if it makes sense for the game that we're actively developing or we're thinking about, you know, it just helps us prioritize things.
How much do you use compute shaders? Do you use them for things besides graphics?
How much do we use compute shaders, and do we use them for things besides graphics?
For things besides graphics, I believe, Andres, you're using compute shader to generate your archives to determine what assets, where do they live on the hard drive to...
Yeah, we used to do that, but we have a lot of things that don't render with compute shaders.
I mean, as far as my domain goes, like pretty much compute shaders are just pure rendering. Yeah, as in something that relates to rendering, GI, ambient occlusion.
So I mean, I think that broadly speaking, right, the question, the heart of that question is do you have spare GPU time? Are you not? Are you Are you not drawing so many things that you can use it for other stuff, right? And I think the answer is no.
No, it's,
right?
Yeah, we're always hurting for GPU time.
You know, you're very much focused on pushing the GPU and the art side, and so that's always full, and even it's over full, right? Spilling out into how much time we're spending on the CPU side in terms of rendering, and that is itself its own bottleneck. So there's no spare GPU time.
Yeah, just to drive home that point, we use asynchronous compute shaders on the PlayStation 4 to compute GI, where right after doing the G-buffer and getting all the element of the G-buffer ready, we just kick off the GI, and then we go do lighting, shadows, what have you, and then right before we get to the forward pass, we check, hey, are the compute shaders ready? And sometimes they are ready, which is fantastic. You know, we managed to hide the cost of GI, like behind a bunch of other work. But some other time in scenes that are super heavy, like tons of shadows and all that stuff, we end up waiting for like half a millisecond, a millisecond, not a second, to actually, for the results to come back, you know, which is still better than not doing the asynchronous compute shader, but it just paints a picture of how busy the GPU is.
Speaking of times, right? I mean, let's talk again. Let's get back to some concrete numbers. Give me a hypothetical frame. How would you sort of break out where the time is spent on the GPU?
All right, so I'm bringing up a scene right in front of me. We're looking at a crowd, buildings, cars moving. We have right now 6 millisecond for static G-buffer things. Static G-buffer things meaning building, lamps, roads, and about 3 to 4 milliseconds for dynamic things. We're talking about pedestrian, things that move. Shadows, we optimize shadows. We have the cascaded shadow maps to render to the 4 or 5 or 6 level of cascades. We spend about 2-3 milliseconds there. Alpha is always like kicking us around a bit, you know, smoke, explosions, and things like that. I mean, we do a bunch of techniques just to try and reduce that cost and throttle like the number of things that we spawn based on the GPU time. So let's say 4 or 5 millisecond post-processing 2 milliseconds, and soon you see yourself at 33 milliseconds, and that's all your GPU time.
All right. Well, on that note, thank you for your time.
Oh, thanks.